Assalamualaikum warahmatullahi wabarakatuh and hello everyone. In this video, we're going to learn the second part of 4.3 orbital hybridizations. We have done with orbital overlapping. Now let's look at what does orbital hybridizations means. Hybridizations of orbital means we're going to mix a number of orbital to form a totally new orbital called hybrid orbital. So the name of hybrid orbital itself also different from the one we have learned in chapter 2. When is it necessary to form hybrid orbital? So there are two cases when hybrid orbital is needed. Hybrid orbital is needed when your molecule has central atom or atoms. So this is a must because we know central atom will share more than one electron with neighboring atoms. For the second case, when you already have central atom in your molecule, at the same time, your molecule has multiple bonds that connecting the terminal atoms. When determining type of hybrid orbital, you should include any sigma and lone pair electrons present in your valence shell. There are 5 types of hybrid orbitals you need to know. The first combinations is by mixing one s orbital and one p orbital to form 2 equivalent sp orbital. Note that the number 1 in here do not belong to the principal quantum number or the shell. It's just tell you out of the 3 orbitals of p, only one of them will involve in these combinations. So once hybridizations happened from initially different orbitals, they are going to form a new hybrid orbital called sp orbital. Each of these sp orbital consists of 50% s and p character. So once these two orbitals get closer, the small lobes here will be overshadowed by these big lobes, hence forming a linear molecule with an angle of 180 degrees. Second type of hybridizations is by mixing one s orbital and 2 p orbital to form 3 equivalent sp2 orbital. Once all the sp2 equivalent orbitals gets closer, they will form trigonal planar molecule with an angle of 120 degrees. The third hybridizations involve when one s orbital mixed with 3 p orbitals to form 4 equivalent sp3 orbitals. When all these equivalent orbitals align, they form tetrahedral molecule with an angle of 109.5 degrees. The fourth type of hybridizations is by mixing one s orbital, 3 p orbitals, and another 1 d orbital. So all these combine to form 5 equivalent sp3d orbitals that finally rearrange to form this shape. So the name of shape formed in here is same as in the 5 electron group arrangement, which is trigonal bipyramidal with an angle of 120 degree and 90 degree. Last but not least, when one s orbital, 3 p orbitals, and 2 d orbitals combine, they will form 6 equivalent sp3d orbitals. From these combinations, an octahedral molecule with angle of 90 degrees will be formed. Here are the steps to form hybrid orbital before we can proceed to the final step showing overlapping of orbital. First, you need to make sure that you have formed the most plausible Lewis structure. Then, by using Vesper theory, you can determine the molecular shapes. The shape of molecule is determined by hybridized orbital. As mentioned earlier, hybrid orbitals can be formed from central atom and terminal atom that has pi bond. So we're going to look at a number of examples in a bit. Each sigma and pi bond will be counted as single electron, while lone pair is still a pair of electron. Knowing number of single electron and lone pair present will help us determine the type of hybridizations as well as the mode of overlapping, either end-to-end or side-to-side. Only sigma and lone pair electrons will be hybridized, while pi electrons will be left unhybridized. Once atoms to be hybridized and unhybridized are determined, we'll proceed to the next step, which is drawing the orbital diagram for each of them. For hybridized orbital, there are 3 states to be done. Ground state, where the initial valence electrons to be located. Then, we have excited state, where locations of electron will be repositioned to accommodate how many sigma, pi, and lone pair an atom has. It is not necessary for electron to change their locations at this step if all the electrons already tally with the type of hybridizations they are going to form. Lastly is the hybrid state, where it will be only two types of orbitals to be formed, hybridized or unhybridized. They will be grouped together. For unhybridized orbital, which mainly terminal atoms, only ground state is needed. Let's apply all the steps we have learned just now into few examples. For the first example, we are going to look at a molecule with only one central atom and contain only sigma bonds. Always starts with the most plausible structure. So we have phosphorus with 5 valence electrons, and then 5 bromine atoms with each 7 valence electrons will contribute another 35 electrons. So it gives a total of 40 electrons. Then we're going to draw the skeletal structure for PBr5. So this 5 bonding pair indicates we are going to deduct another 10 electrons from the total of 40. So we are now left with 30 electrons. Then these 30 electrons will then be distributed to the 5 bromine terminal atoms. Each will receive 6 electrons. And lastly, 0 electrons left. So you need to check the formal charge for phosphorus. Phosphorus got 5 valence electrons to be minus with 5 bonding pair electrons, so altogether 0 formal charge. And for bromine, they got all same environment. So each bromine got 7 valence electron minus with 6 lone pair electrons and 1 bonding pair electron, altogether 0 formal charge. Hence, this is the most plausible structure due to 0 formal charge on all atoms. Since this molecule has only one central atom and has no pi bond connected to central atom, means the shape of molecule will be determined by only central atom. So this 5 electron group surrounding the P and all are bonding pairs indicates both electron group arrangement and molecular shapes is trigonal bipyramidal with a bond angle of 120 degree and 90 degree. So from this structure, we know we have 5 single bond, tells you there are 5 sigma bonds, no pi bond or no lone pair. So each sigma bond indicates single electrons. So there will be 5 single electrons to be formed in the phosphorus orbital diagram. Hybrid orbital only occupies sigma and lone pair electrons. Therefore, the type of hybridizations will have a combination of 5 orbital, comes from 1s, 3p and 1d, hence giving hybrid orbitals of sp3d. Phosphorus is located in period 3, group 15, with valence electronic configurations of 3s2, 3p3. At the moment, this orbital diagram contains only one lone pair and 3 single electrons. Phosphorus as central atom in PBr5 require 5 single electrons as suggested by the 5 terminal atoms to be paired with. So, to ensure there are 5 single electrons, one of the lone pair in 3s orbital will excite to a higher energy level. Since the principal quantum number 3 can have up to d orbital, then this one electron will excite to 3d orbital. As hybridized orbital takes only sigma and lone pair electrons, hence all 5 sigma electrons in here will be hybridized as sp3d orbital, and the rest of 3d orbital here will be left unhybrid. For terminal atoms that do not undergo hybridizations, their overlapping of orbital will involve only unpaired electron from s or p orbital. So bromine with valence electronic configurations of 4s2, 4p5 will have 1 unpaired electrons at each 4p orbital. So makes a total of 5 unpaired electrons contributed by 5 bromine atoms. Next, we are going to show the overlapping of orbital for this molecule involving hybridized and unhybridized orbital. So we'll start with sp3d orbital of phosphorus with 5 unpaired electrons. Overlap with 5 unpaired electrons comes from the 4p orbital of Br. So the mode of overlapping takes place in here is end-to-end. Therefore, 5 sigma bonds are formed. So make sure the electrons are paired with opposite spin. Second example, we are going to look at a molecule with central atom and its terminal atom connected to central atom by pi bond. So first, we need to count the total valence electron contributed by 1 nitrogen, 1 carbon, 1 oxygen, and 1 negative charge. So altogether giving us 16 electrons. The carbon will be the central atom due to the least electronegativity among all other atoms, hence forming 2 single bonds with terminal atoms of nitrogen and oxygen. So by having these 2 bonding pairs, 4 electrons will be deducted from the total valence. Lastly, we have 12 electrons. The remaining 12 electrons are distributed to nitrogen and oxygen with 3 lone pair each, so no more electrons left. You need to check if the central atom already achieved octet or not, since they are located in period 2. So if not yet octet, we need to form multiple bonds that can be formed by donating the extra electrons on the terminal atoms. We will have a number of resonance structures to be formed, but after priorities to form most plausible structure has been taken into considerations, structure with carbon triple bond nitrogen and carbon single bond oxygen will be the most plausible structure because the more electronegative atom, which is the oxygen, got the negative formal charge. So the shape of molecule is determined by hybridized orbital. Since this molecule has a central atom carbon and at the same time has a pi bond connecting terminal atom nitrogen to carbon, means we also need to look at both atoms. So both carbon and nitrogen will undergo hybridizations. On the other hand, oxygen atom do not undergo hybridizations because it's just terminal atom and has no pi bond connected to carbon, which is a central atom. Carbon with 2 electron group consists of 2 bonding pairs. One comes from the triple bond, another one comes from the single bond. Hence, electron group arrangement and molecular shapes will be the same, which is linear with one angle of 180 degrees. So from this structure, we could see we have triple and single bond. All first bond is considered sigma, while the second and third will be the pi. So we have a combination of 2 sigma and 2 pi in here, means we're going to have 4 unpaired electrons to be accommodated in carbon orbital diagram. Since hybridized orbital only takes sigma and lone pair into considerations, hence these 2 sigma electron will form sp hybrid orbital and these 2 pi electrons will be left unhybridized. Carbon with valence electronic configurations of 2s2, 2p2 contains 1 lone pair and 2 single electrons in its ground state orbital diagram. So from the information we have gathered just now, this carbon requires 4 single electrons to form 2 sigma and 2 pi. So one of the lone pair in this 2s orbital will excite to a higher energy level of 2p orbital like this. Lastly, these 2 single electrons will occupy this sp hybrid, while the other 2 single electrons occupy the unhybridized orbital. Just to remind, unhybridized here means they still overlap if they got electrons, just like these carbon hybrid states. But then the overlapping just happened between the p orbitals. Nitrogen with 2 electron group consists of 1 bonding pair comes from the triple bond and 1 lone pair. Hence, the electron group arrangement and molecular shapes will be the same, which is linear with bond angle of 180 degrees. So from this structure, we could see we have triple bond and lone pair. So the first bond is considered sigma, and the second and third will be the pi, while the lone pair is still a lone pair. So we have 1 sigma, 2 pi, and 1 lone pair around the nitrogen atom contributes to 3 unpaired electrons and 1 lone pair. For hybridized orbital, we are going to form for this nitrogen. We are going to take this 1 sigma and 1 lone pair, combine together to get a new hybrid orbital of sp, while these 2 pi electrons will be left unhybridized, just like in carbon just now. Nitrogen with valence electronic configurations of 2s2, 2p3 contain 1 lone pair and 3 single electrons in its ground state. So the number of sigma and pi and lone pair just now already tally with the electronic configurations in its ground state. So for excited state, no need to excite the electron in here. While for hybrid states, one single electron from this one sigma and one lone pair will combine to form sp hybrid, and the other two single electrons comes from the pi electrons will be left unhybridized. For oxygen minus that do not undergo hybridizations with 7 electrons in its valence shell, the overlapping of orbital will involve only one unpaired 2p orbital. So, the overlapping of orbital for this molecule will involve both hybridized and unhybridized orbital. We should start from this central atom carbon with sp orbital to overlap with this terminal atom nitrogen, also with sp orbital. So each will contribute one unpaired electrons with opposing spin to form sigma bond. Next, carbon and nitrogen also connected by 2 pi bond. So we are going to expect side-to-side overlap to take place twice. Make sure the 2p orbital of carbon is perfectly aligned with the one you want to overlap. Means, if your carbon have it tilt to the right, the other 2p orbital on nitrogen also need to tilt a bit right. So both of these orbitals should carry different spin of unpaired electron, hence pi bond is formed when you cross them together like this, ups and down. And then another side-to-side overlapping also involve 2p orbital on carbon and 2p orbital on nitrogen. So the other orbital should be drawn tilting to the left because we don't want these two to collide with one another. And look at your sp orbital of nitrogen. They are contributed by another lone pair in here. So don't forget to include your lone pair in here. So we have done all the orbital overlapping involved in carbon and nitrogen. Moving on to this oxygen minus. So this oxygen minus has single bond with carbon. So this one unpaired electron contributed by sp orbital of carbon will overlap with one unpaired electrons on 2p orbital of O minus. Don't forget to include O minus in here because the number of electrons already changed. Hence, forming the sigma bond between sp orbital of carbon and 2p orbital of O minus. For the third example, we're going to use CH3 and H2 to cater molecule with multiple central atoms. So the total valence electron contributed by 1 carbon, 1 nitrogen, and 5 hydrogen will be 14 electrons. So carbon and nitrogen will be the central atoms, while hydrogen will be the terminal atoms because they can only achieve duplet. So there are 6 bonding pair altogether, means 12 electrons will be deducted from the total valence electron, left with only 2 electrons. These remaining 2 electrons will be given to nitrogen because carbon already achieved octet by having 8 electrons surrounding it. If we check the formal charge for carbon, we also get 0 formal charge comes from 4 valence electron minus with 4 bonding pair electrons, altogether 0. But don't forget to check for nitrogen as well. So nitrogen with 5 valence electrons to minus with 3 bonding pair electrons to minus with another 2 lone pair electrons, so 0 and 0, giving the most plausible structure for CH3 and H2. The shape of molecule is determined by carbon and nitrogen since they are both central atoms. So carbon with 4 bonding pairs tells that both electron group arrangement and molecular shapes is tetrahedral with angle of 109.5 degree between the bonds. So this 4 sigma indicates 4 single electrons. Hence, this 4 sigma will be counted as the sp3 hybridizations. Nitrogen also has 4 electron group which give rise to electron group arrangement of tetrahedral. Due to 1 lone pair on nitrogen, so greater repulsion is expected from lone pair bonding pair electron repulsions. So making the shape change a bit from tetrahedral to become trigonal pyramidal with bond angle expected to be less than 109.5 degree. So all sigma bond, in here we have 3 sigma bond and 1 lone pair will undergo hybridizations. Therefore, sp3 orbital of nitrogen is formed. Carbon with valence electronic configurations of 2s2 2p2 contain 1 lone pair and 2 single electrons in its ground states. So from the information we have gathered just now, carbon requires 4 single electrons to form 4 sigma bond. So one of the lone pair electrons in 2s orbital will excite to a higher energy level of 2p orbital like this. So we now have 4 single electrons. And then these 4 single electrons will combine to form sp3 orbital of carbon. As for nitrogen, nitrogen got valence electronic configurations of 2s2 2p3, contain 1 lone pair and 3 single electrons in its ground state. So the number of sigma, pi and lone pair just now tally with the electronic configurations in the ground state. So there's no need for this ground state nitrogen to excite to a new energy level. So they will remain as it is. And then at the hybrid state, 1 lone pair and 3 single electron will form sp3 hybrid orbital. The 5 hydrogen atoms will contribute 1 unpaired electron each from 1s orbital to form a total of 5 sigma bonds with carbon and nitrogens. So the overlapping of orbital will start from the 1 sp3 orbital of carbon to overlap with 1 sp3 orbital of nitrogens and then to form sigma bond. There are still 3 unpaired electrons on 3 sp3 carbon and 2 unpaired electrons on 2 sp3 nitrogens. Note that one of the sp3 nitrogens is filled with lone pair. So all these 5 unpaired electrons on carbon and nitrogen will overlap end to end with 5 1s orbital of H, therefore forming 5 sigma bonds altogether. That's all for orbital hybridizations, and that marks the end of subtopic 4.3. Thank you for your attention. Goodbye.